seconds and then start when this thing clicks at 40. Okay, so what I will emphasize to everybody in the class is this is a capstone class. It is something that involves system programming. It is something that involves C and C++. I've had cases in which the number of students has dropped down into the 20s, other cases in which the number of students has been in the 40s, or in the mid-30s, and hope that people are comfortable with their teams and will be able to go forward with the teams that they currently have. This is a much more fun lecture than the previous one because instead of going backwards, as we did going back from B-trees to ISAM, we're going somewhat forward. There's a lot involving hashing that goes beyond what's described over here, especially with distributed hashing. But this is a lot more fun and involves aspects of hashing that you may not have seen before. And as usual, I'll emphasize the chapters cited are there on the first slide, so you should be able to know where those are. In terms of the project, everybody knows about Project 2. I was answering a few questions about Project 2 before the class started. Lab sections, you'll get a chance talking to both Saloni and to Matthew to ask a lot of questions about it, so please see about attending. If you haven't read Project 2 yet, please do it. As I discussed last time, it involves completing the RBFM, the Record-Based File Manager, having a record manager. Record-Based File Manager deals with records. There are a lot of things inside RM that deal with tuples instead of records. They're a different layer of how you're approaching it, but the tuple-based stuff leverages the record-based stuff, just as the record-based stuff use the page file manager. And besides having a record manager, you have to think about the catalogs, and the fun part about catalogs is bootstrapping them, because the catalogs describe all the tables and attributes, including the tables, the system catalogs that tell you about the other tables and attributes. So the tables about catalogs and attributes don't only tell you about the tables that you create, but also the actual tables that tell you about the tables and attributes. So again, catalog tables are the ones that tell you about all the tables, including themselves, and bootstrapping that is kind of interesting. Emphasis, as the assignment says, you can insert, update, and delete all the tables except the system catalogs. The system catalogs get having changes made based on as side effects of things like creating a table or dropping / destroying a table. They don't get up. You're not allowed to insert, update, and delete. And so one of the things you have to figure out is how you prevent that. How you prevent somebody from doing an insert, update, and delete on the tables table, for example. You may use our Project 1 solution, or you may use your own. If you use ours, you'll have to learn our code. If you use yours, then you'll inherit any bugs that you previously had, as opposed to inheriting our bugs. And there was a fairly detailed note about forwarding addresses that was posted that hope people have looked at. Forwarding addresses are one of the more amusing things inside this assignment, e.g., how do you make sure that you don't keep forwarding forever? You would have nonlinear time if you have to move a record off the page it started with, and then in turn have to move it off that page because it got forwarded again. How do you make sure that you don't have a long chain of forwarding addresses? And it's actually pretty easy to do. There is a midterm that's coming up. This is week 4. 10 midterms stink. Pick your own favorite word for that, but we're going to be hitting the midterm 2 weeks from today. And as usual, no makeups, no early, no late, no devices, the usual rules on that. You can bring in a cheat sheet with whatever you want on it, no sharing. This morning I posted the midterm from last year, so you have a chance to look at that. I will post the solution to that next week. We haven't gone over all the material that's in that midterm, but we've gone over a fair amount of it. My usual suggestion, instead of waiting for the answers to come up, try taking the exam, because as you probably saw in 180, it's more valuable to look it over and see where your errors are. Of course, it won't be exactly the same thing on this year's midterm, but as you will see, a number of the questions relate to the projects. Surprise, surprise. So you're working on the projects. Two advantages. One, you learn the material that is required in the course, including for the exams, and the other is that it helps keep a team balanced if everybody's working on the team. And again, most, except for the codas, most of what we discuss in class is discussed inside the textbook. It is a good textbook of slightly ancient, which is why I often have the codas. Ancient meaning 15 to 20 years old. Please read the textbook as well as the lectures if you have questions. There is a lot of material in the course. Come to office hours. I'll be happy to talk to you about the lectures as well, but the textbook can help, and we can go over stuff in the lecture. Fast reminder. We have three approaches 1, 2, and 3 for representing this thing that we call data entries. So you have a search key K. The data entries could include the actual data, and they also could include search key and RID. And approaches 2 and 3 are effectively the same thing. A little subtle implementation difference. In approach 2, you have search key and RID, search key and RID, which means the same search key appears a lot of times. California, you're repeating it a lot of times. All the students, records for all the students located in California. Whereas the other approach has the search key once and then all the RIDs that correspond to it. We've talked about advantages and disadvantages to the two different approaches, but the choice is orthogonal. And we looked at hashing as well as trees. And hashing, which is great for dealing with equality, it's a little bit strong to say it can't deal with range searches if, again, your range is small and discrete. It's easy to deal with it. I only have 26 letters of the alphabet and single character things. I'm looking for everything between B and F. Then I could use hashing to look up B, C, D, E, F. But in general, it's not good for ranges, e.g. the salary example that I always give. And last time we did this going backwards in time. We took our DeLorean from 1985 and went back to 1955, where we looked at the situation on B trees, where we started with a dynamic tree approach. And we went backwards in time and looked at something that preceded it with something called ISAM, which is very good for trees if your data isn't changing very often, but it can end up quasimodoing, leaning to the right, if you end up having lots of inserts going in one direction versus the other. Whereas B trees, B plus trees are self-organizing, and you always have log complexity to be able to search them. And we looked at hashing as well, but we started off with static hashing. And one of the two topics we'll be talking about today is a dynamic hash table. A hash table that dynamically changes what's going on as new entries come in, and it can be much better than the static hashing approach. So what was static hashing? The way that we dealt with it was there are two usual ways of dealing with static hashing that you've probably learned in things like 101. One is by using the approach that we described, where you have overflow pages. So you have M buckets, and we'll call them buckets 0 through M-1. And if a bucket can hold a number of values in it, again, approaches 1, 2, and 3. The things you put in the bucket could be the data, or it could be key RID or key RID list. You could put the data in there. Or you could go ahead and have key RID, key RID, key RID. So all that approach exists. And then if the bucket fills up, then you have an overflow page. And of course, if you have a lot of overflow pages, then the value of the hashing diminishes. So it's great when you have a terrific hash table, and it ain't so good if you've got lots of overflow pages. The other approach that's often used is called open addressing, where it might be just try to find the next place in the hash table where there's a value, or use a quadratic rather than simple linear approach where you use squares. So you try to find the place for it, and if it doesn't fit inside, you put it in +1 squared, then you try +2 squared, +3 squared, +4 squared. And again, I hope you learned a variation of that in 101. It gets kind of tricky when you do deletions, because you have to mark that the place was filled. So just as a fast comment about the open addressing approach, if I'm using a quadratic, so I'm putting something in the table at a particular place, h of x, h of key, and if that doesn't work, I try h of key +1, then h of key +4, then h of key +9, then h of key +16. Then I can find it if it's in there, but might have to search a lot of different places, and it might interfere with the values that really were supposed to go in h of key +16. And also, what happens if I delete the value that's at h of key +9? I have to mark that it used to be occupied, otherwise I won't look at h of key +16 or h of key +25. So I have to keep something in the h of key plus 9 which says, don't stop here. You stop when you come to an empty slot. So again, if there's something past h of key plus 9, I either reorganize or I march the h key of 9 as saying it was occupied. So keep looking, because there might be something in 16 or 25 or so on. Stuff to play with in that approach. Again, not for a database course, but in general about data structures. Anyway, the static hashing with overflow pages and the open addressing can get kind of bad. The overflow pages, because you could have a lot of overflow pages. And because you may size this expecting that I'm going to have 1,000 things in my hash table and I've got 10,000 things in my hash table. It gets kind of bad. And the open addressing, because conflicts and long chains, in fact, where I have puns. As you know, I like puns, but not the puns in the hash table, where it makes me have to search through a lot of the hash table that's irrelevant to the value that I'm looking for. So again, hashing is terrific when you size it properly, and it ain't so good when you size it properly. So the buckets contain data entries, which can be any of the approaches 1, 2, or 3. The hash function, one of the typical approaches of doing hashing is to pick a value m that's a prime, and often what you end up doing is, let's say, taking things mod m to be able to do it, and a function that often works is a non-zero. Take a times the key plus b as being your function, then take that mod m, modulo m, and use that. And there are really good what are called so-called universal hash functions that are really good for spreading things around. And again, this gets discussed in 101. I taught 101 last quarter and taught it, so I hope that you're familiar with that idea. But you can, no matter what great approach you have, you can get long overflow chains if you pick the value of m, and you get a lot more data. As I said, 1,000, you have 10,000 or 100,000 or something having size m, things get big. So there are two techniques that are frequently used. One is called extendable, not extensible. I will sometimes say extensible, but it's extendable. And you'll see it extends. You'll see why it's called that. Extendable hashing and linear hashing are great techniques for dealing with this. Linear hashing is discussed in the textbook. We're not going to be talking about it on these slides, and we'll see how extendable hashing works. So basically, you get buckets, which are the primary place where you put values. You could have overflow. The buckets become full. So here's an obvious solution. Double, toil and trouble. Doubling the hash table might help whenever things become full. But that's going to be kind of bad, because you're going to have to take all the data and deal with finding whether it belongs in the one page or the other page. So mucking with the data when something goes wrong, we have to touch all the data. It could be like a lot of data. We're going from 1 million up to 2 million or whatever it is. Touching all the data because a bucket becomes full is kind of expensive. And burps, vacuuming and garbage collection and all those other burps are things where you don't want to go ahead and make people happen to wait periodically. You'd like these things to be something where you don't pay a whole lot of expense when there's a problem. So having to go through all the data and reorganize it one of 2 pages, it'll be reorganized. It'll be better going forward, but that burp when you reorganize is too expensive. It's a bad idea. Here's a good idea. You have a directory, and the directory points to buckets. And here's what we're going to do when a bucket becomes full. We'll split the bucket in 2. We will kick the bucket and break it into 2. And we'll double the directory. But the only bucket that we have to split in 2 is that bloated bucket that caused the problem. We won't split all the buckets in 2 because they don't need it. Only one bucket is bursting its belt size and needs to be split. That bucket will end up getting split. The directory, which tells you where to find the bucket, is going to be much smaller than the bucket, because there are a lot of different data things in the bucket. So we will split the directory, and we will split the offending bucket, the bloated bucket. But we won't do anything to the other buckets, okay? So there are no overflow pages at all. And how you play with this, that's the trick. That's why it's called extendable. You're gonna be extending, but you're not gonna be paying this huge price of having to go through all the buckets. So let's look at a simple example. This is a steady state for this extendable hashing. We'll talk about what's going on and what happens when data ends up coming in. So we're gonna have a directory where there are gonna be 4 buckets that are in there. And what we're just gonna go ahead and do is we're gonna have those 4 buckets which correspond to buckets 0, 0, 0, 1, 1, 0, and 1, 1. And for 0, 0, and just to keep it easy, we're gonna be looking at values, mod the last 2 bits, mod 4. So the things that will be in the bucket, which is bucket A, which corresponds to 0, 0, are gonna be the things that are 0 mod 4. And for 0, 1, we're gonna have bucket B, which is gonna be all the things that are 1 mod 4. And you've seen the pattern. For 1, 0, we're gonna have the things that are gonna be 2 mod 4. And for 1, 1, we're gonna have the things where the value is bucket D, which is the things that are 3 mod 4. And those are gonna be where you end up having the data entries, which in turn, again, any of the 3 approaches. The data may be in the buckets, or you can have search key, RID, etc. So here's the thing that you're gonna do. You're gonna search for K, and you're gonna use your hash function, which is gonna give you a value, which could be a string of bits. But here, this is important, we're only playing the last 2 bits of the function that we get by taking h of k. H of k gives us a range of bits, 32 bits maybe. But we're only looking at the last 2 bits. Okay? And then, so if we're trying to see whether or not 21 is inside this, well, our hash function is going to give us something that ends in 0, 1. And we're going to look in the bucket that 0, 1 points to, which is bucket B. And behold, we see 21 is in there. But if we've been looking for, say, 29, you take it again, look at the last 2 bits, which are also 0, 1, 29 is not in there. So if we were trying to go ahead and put a value in, here's what you do. There's either room or there isn't, just like in a B tree, just like in our original cache tables where we have to go to overflow buckets, but there are no overflow buckets in extendable hashing. So what are we going to go ahead and do? We'll try to put something inside the bucket. And there are 2 possibilities. Either there's room or there isn't. If there's room in the bucket, put it in the bucket. If there isn't room in the bucket, mitosis. We're going to split the bucket. We're going to split the bucket. And in some cases, but not all, we'll have to double the size of the directory, meaning instead of looking at the last 2 bits, we'll be looking at the last 3 bits of the hash function. Okay? So sometimes we will have to do that, but not always. When will we have to and when won't we? There's a number that you see here that is added on this. There are 2 actually terms that are introduced. There's a notion of local depth and global depth. What does global depth tell you? How many bits you use to find the bucket. What does local depth tell you? It tells you whether or not that bucket has been split into or not. Because remember, it's only the bloated bucket that gets split. The other buckets, when we have to go to 3 bits, will stay so that we're only using 2 bits. Let's see what that means in action. Okay? So we're going to see what ends up happening. In this case, the local depth and the global depth are identical. Everything is based on 2 bits. Okay? So now let's suppose that we want to put 13 inside the table. And we have a hash function which, gives us, let's say, I'm not going to show you 32 bits, it's 1101. We're only using the last 2 bits. 01, we're going to get pointed to bucket B. Is there room in bucket B? Yeah. The entries corresponding to 13 are put inside the bucket. Cool. That was easy. You know what's coming. Okay, so you know the hash function, it's just something really simple. We're just taking the binary representation. Okay, now let's suppose we put in the value 20. Okay, let's see what ends up happening with that. It's still the same kind of thing. So what are we going to do? 20, we're going to see about trying to put it into the right place. Okay, it's going to try to put it into 20 mod 4, it's going to be 0, 0. The last 2 bits are 0, 0. So we're going to try to hook it into bucket A. No room. Very sad. We don't give up. We don't take our marbles home. We don't create an overflow bucket. What do? We're going to split bucket A into 2 buckets. What's involved in splitting it into 2 buckets? We're going to create a bucket which we're calling A2. It's going to be, again, a split of bucket A. And what stays in A and what stays in A2? You'll notice that there was a change when I did the split. 2 bits wasn't good enough to distinguish A from A2. We have to distinguish A from A2. We're going to use 1 more bit. So we're going to use the last 3 bits to distinguish between A and A2. So this guy, we're going to be using 3 bits. So both of these things have 3. And so what goes in A and what goes in A2? Modulo 8, what gives you 0 and what gives you 4? The last 3 bits. So we're looking at modulo 8 instead of modulo 4. Modulo 8, the things go into bucket A when the value is 0. Modulo 8, again, just looking at the last 3 bits, we're going to put the things inside A2. So basically, the things where the last 3 bits are 0, 0, 0 go into A. The things where the last 3 bits are 1, 0, 0 go into A2. One more time. These things all ended in 0, 0. They were all nicely together in bucket A. Their last 2 bits were 0, 0. They were together in bucket A. But there was no room in bucket A for us to put the 20 in, so we're going to split. We're going to say we're going to use 1 more bit, which distinguishes 0, 0, 0 and 1, 0, 0. All of them have lived happily together in bucket A when the last 2 bits were 0, 0. But now, because there wasn't enough room in bucket A, we're going to be using 3 bits, and 0, 0, 0 as the last 3 bits is different than 1, 0, 0. What goes into bucket A? The things which give us 0, 0, 0 as the last 3 bits. And that's the 32 entries and the 16 entries. What goes into bucket A2? It's not randomly determined. It's based on the things that correspond to 1, 0, 0. They lived nicely together when we were just using the 0, 0, but now they're separated out. And what goes into 1, 0, 0, the bucket for A2? 4 and 12 and 20, the things that are 4 modulo 8. So that's all very nice. But look at what's going on. What we're saying is we change the local depth of those 2 buckets to say we're using 3 bits, not 2 bits. Something else has to change. Several something else's have to change when we do this for this to work, for the strategy of looking things up to work, the search to work, because we have to distinguish. Before, the 0, 0 had pointed to bucket A. Not good enough. We have to distinguish between A and A2. We need 3 bits, not 2 bits. Guess what happens? We have to change the directory. We have to double the size of the directory. Because we got to use 3 bits instead of 2 bits. We only took the bloated bucket and split it in 2. So let's double the size of the directory. We now have a directory that has 8 entries in it instead of 4. And notice that we're now saying we're using 3 bits. The global depth is 3. The global depth is going to be greater or equal to all of the local depths. It's going to be the biggest value of all the local depths. And what do we point to? Well, as you would guess, the 0, 0, 0 is going to point to bucket A. The 1, 0, 0 is going to point to bucket A2. What about the other directory entries? Because we didn't split any other buckets except for the bloated bucket. There's a hole in the bucket, dear Liza, but only for that one bucket. So we can distinguish between A and A2. We have to distinguish between A and A2. Because if we're looking for 12, we want to look down in A2. And so we'll do that. Because the hash function, the last 3 bits will be 1, 0, 0. If we were looking for something like 64, we'd be looking in bucket A. It's not there, but we'd be looking for the entries for 64 in bucket A. What about the other 6 buckets? 0, 0, 1 and 1, 0, 1 both point to bucket B. Before, they had lived together nicely in the directory in the single bucket for 0, 1. But bucket B hasn't been split. It did not undergo mitosis. Both of those directory entries point to where 0, 1 had pointed before. When I say pointing, it's just, it's just a bucket number. I'm calling them A, B, C, D. It's just a bucket number. It's just a bucket they point to. And the same thing for 0, 1, 0 and 1, 1, 0. They both point to bucket C. And of course, the same thing also for the green arrows, 0, 1, 1 and 1, 1, 1. They point to bucket D. Does all this work? Yeah. I mean, suppose that we were looking for 19, then 19 is going to be something where, it's going to correspond to, 1, 1, 1. So for 19, we're going to be looking at the last 3 bits. Again, it's a stupid function, but it's a simple one. We're just looking at the thing in binary and using the last 3 bits. The 1, 1, 1 is going to point us to bucket D. But so is the 0, 1, 1. So we have doubled the size of the directory, but only one bucket got smashed into. Question?
How are we going to split the bucket B, for example? Because won't we have the... Okay, never mind.
No, keep going.
Because what if the modulus of... Because it's bucket B is going to have 2 different moduluses in there.
True. How are we going to split bucket B? Great question.
We're going to have to change the global depth of 4.
Nope. Splitting bucket B is not going to change the depth. And funny that you ask about that, because guess what's coming next? Everybody okay on this before we split B? So we did have to split the directory, but only one bucket got split. Changing the directory is something that can be done fairly quickly. So, does splitting a bucket always require doubling the directory? No. Because let us suppose that we had to split B. So we'll create buckets B and B2. Stupid names, but easy to remember. We can do that by having 0, 0, 1 and 1, 0, 1, which are currently both pointing to B. One of them points to B and the other one points to B2. And we only need 3 bits to do that. So the local depth for B and B2 would become 3, and the global depth would stay 3. One more time. If I end up putting, let's say, a value like 17 into bucket B, 17 star. There's no room to put 17 star inside B. B is going to get split into B and B2. The local depth will then become 3. But the global depth was already 3. The directory didn't have to change other than having the difference between B and B2. Currently, 0, 0, 1 and 1, 0, 1 both point to bucket B. If I'm splitting into B and B2, then I would have 0, 0, 1 point to B and 1, 0, 1 point to B2. And I'd split B based on whether or not the last 3 bits are 0, 0, 1 or 1, 0, 1. And now, change, again, is take the bloated bucket and split it. But, and I also had to change the number of bits used for the local depth to 3. But I didn't have to change the local depth, and I didn't have to double the directory. Changing the global depth to 3 and doubling the directory come together. That when I have to do that, I have to do that. So only when you split a bucket that's at the maximum size do you have to go ahead and double the directory and increase the global depth. Because when you split the bucket, you have to increase its local depth, and the global depth has to be more than the local depth. The global depth tells you how many bits do you have to look at to be able to figure out where to go. Question?
What if splitting the buckets doesn't fix your problem? Because what if the last 4 bits of all the numbers in B are the same? Everybody's gonna end up back in B1, and B2 is gonna be empty.
Let me get to that.
Okay.
I will. There's one minor serious problem with this that in fact is a problem for any kind of hashing approach, and I'll come to that in a second, and I'll deal with your point, which again sometimes can be dealt with easily and sometimes can't. Suppose that, well, let me talk about what's in blue before I get to what's in green. How do you double the directory? The way that you do it is and this is an important systems implementation point, is I doubled the directory. I'll go back to the previous slide. I take my directory and I do a memcopy of my directory, assuming that there's enough space immediately after, or if not, I do a memcopy of it twice to the place where I have enough space. The new directory is exactly the same as the old directory, except it's cloned. It's got a duplicate. It's got a twin next to it. That's exactly the same, except that I've increased the global depth to 3, and I had to change the pointers for the bloated bucket. In other words, the new directory that you'll see on the next page is exactly the same as this one, duplicated and with the update only for the bloated bucket. So it's exactly the same as what we had. It's exactly the same. In particular, the old green arrow and the new green arrow point to the same place. So when I copy over, it's exactly the same. The red arrows stay the same. The black arrows stay the same. It's only the bold black arrow that ends up changing for A and A2. So copying over that directory takes care of everything except for the bloated bucket, which split it in 2. So I can do this with a simple memcopy. This is why, by the way, to answer the question that's in green now, this is why we use the least significant big digits instead of the most significant, because you couldn't use that nifty memcopy trick if you used the most significant. You could do it, it would just be a little more awkward as code to be able to do it. It's not hard. You just have to alternate, where you put things. It's a little uglier. So it's actually better to go ahead and do the thing with the memcopy, just a simple system trick. Okay, so if you use the most significant, again, it wouldn't be hard to do, you just couldn't use that simple memcopy trick. Okay, so the last 2 bits told us whether or not something belonged in A or A2. When there was a single A, we knew that the things belonged in the same bucket when A wasn't split. But when A was split and we needed to distinguish between A and A2, we needed to be able to have the 3 bits. Now, basically, 2 bits tell us it's either A or A2. And again, before the mitosis, not distinguishing was okay. And having only one version of B, just having B, not having B2 was fine. But the 3 bits were needed when we did the mitosis. So we will always use the 3 bits, even though the local depth is 2. It's just that only, before B was split, B and B2, there wasn't a separate B2. It was all in the same place, again, showing over here. Before we had to split B, everything got put into B. The pointers for 0, 0, 1 and for 1, 0, 1 pointed to the same place. So the global depth tells us how many bits you got to look at, and the local depth tells you Was I split? Local depth tells you whether or not you were split. The local depth can be less than the global depth, as we've seen. So you have room to do splitting if the local depth is less than the global depth. When does a bucket split cause the directory to be doubled? Only when the local depth of the bucket that you're splitting is equal to the global depth. So if the global depth is 3 and I have to split a bucket whose local depth is 3, I gotta double the directory and go to 4. And per your question, sometimes you can have a situation where splitting isn't good enough and going to 3 isn't good enough, so maybe I gotta go to 4. Okay, but we'll come to an interesting case in a second. So it's only when I have to split a bucket whose local depth is equal to the global depth that the directory as it exists won't accommodate, so I gotta double the directory, I gotta split the directory, split infinity for those of you who are pre-Xanthine fans. What happens when a bucket splits and its local depth is less than the global depth? You don't have to split. The directory can accommodate that. There's 2 separate entries, at least, that I have to deal with it. But if the insert causes local depth to become greater than global depth, then I do that copy over trick, because I'm using the least significant bits. And then I've got to fix the pointer between B and B2 if I'm splitting B. Question on this? It's kind of pretty. It's a combination of a very nice algorithm from a math standpoint and from a system standpoint. Very efficient. And again, it's self-adjusting, autonomic. Of course, if you split the directory, you always have to fix the global depth. Global depth tells you how many bits you need to use. Global depth always has to be greater or equal to all the local depths. And of course, the local depth for the bucket that you ended up, you had A and A2 having depth 3, now you have B and B2 having local depth 3, and of course global depth 3. But you may have to go to 4, as pointed out, in case, 3 bits isn't good enough. How many disk accesses or whatever persistent storage you have would you need for this? Well, if the whole thing fits inside memory, then it's not an issue. But if the directory fits inside memory, then you would only have to do the adjustment of the write to for the actual for the actual read. If the entire stuff in the directory fits inside, then you just have to be able to do the read. If the directory is not memory, you may have to read the directory. Typically, the directory will fit inside memory. And in fact, the hash table itself will often fit inside memory. It's only maybe going after the data, you may have to go out to add an SSD. And if there's more than one entry matching a key, and there can be, then it may be more than that to be able to actually get the data. Notice that the directory does grow in spurts, and there is this bad case that I promised I would tell you about. If you have very skewed data, if you pick a reasonably good hash function, you're not going to end up having that many puns on the data. You better be careful to pick a good hash function. For example, you probably don't want to use character strings where you use the first couple of letters of the character